Okay, why don't we get going? Okay, so today we're going to talk in this hour about the ionic mechanisms of the action potential. So is it possible to describe the ionic mechanisms of the action potential in great detail as it was possible to describe the ionic mechanisms for the resting potential? And can we answer the questions that came up in the last lecture? What is the mechanism that is responsible for the depolarizing phase of the action potential? What is the mechanism responsible for the repolarization of the action potential? Why is the action potential only 1 millisecond rather than 100 milliseconds? What is the mechanism that accounts for the after hyperpolarization? Back when Bernstein was proposing his hypothesis for the ionic mechanisms of the resting potential, another early physiologist by the name of Overton was making some intriguing observations showing that nerve and muscle cell excitability was dependent on the extracellular concentration of sodium. That idea was picked up later on in the 1950s by a group consisting of Hodgkin, Huxley, Katz, and colleagues. And what they did was to formulate a hypothesis for the ionic mechanisms for the action potential. And what they said was that the membrane potential at the peak of the action potential was equal to, and we'll put a question mark here, it was equal to the sodium equilibrium potential, which is equal to 60 times the log of the outside sodium concentration divided by the inside sodium concentration, right? So, interestingly, the peak amplitude of the action potential approaches the value of the sodium equilibrium potential, which if you plug in these numbers, you come up with a value of plus 55 millivolts. That means if the membrane was only permeable to sodium and no other ion, you would have a potential difference across the membrane of plus 55 millivolts. The peak amplitude of the action potential approaches that value, so maybe the peak amplitude of the action potential is due to the fact that the membrane during that transient phase is becoming highly permeable to sodium and essentially swamping out that resting leakage of potassium, which is underlying the resting potential. So Hodgkin, Huxley, and Katz, they went on to test this hypothesis, and they did kind of an equivalent experiment on what was done to test the sufficiency of potassium ions for the resting potential. So the fact that the peak amplitude of the action potential was near the equilibrium potential for sodium, that was the necessity part of it, but the sufficiency comes out if you alter systematically the extracellular concentration of sodium and see how that affects the peak amplitude of the action potential. So there's 3 panels here. In each one you have a normal action potential. That means normal extracellular sodium. Here's the initiation phase, the depolarization phase, the repolarization phase, the after hyperpolarization. So in 3 cases you have the control, and then you also see the consequences of systematically varying the extracellular sodium concentration, 70% normal, 50% normal, 33% normal, and I think it's clear that as you reduce the extracellular sodium concentration, reducing the equilibrium potential for sodium, you see that there's a decrease in the peak amplitude of the action potential. Next slide, you plot those measurements. Here's the peak amplitude of the action potential in this axis. Here is the extracellular concentration of sodium. Here are the measurements. At this concentration of sodium, you have this peak amplitude of the action potential. As you reduce the concentration of sodium, you see that you reduce the amplitude of the action potential. Here is the straight line predicted by the equilibrium potential for sodium, this red line. So the good news is that there is an excellent agreement as you change the sodium concentration, the peak amplitude changes. as does the equilibrium potential for sodium. But there's a deviation between what you measure and the predicted value. Now, that's actually not too disturbing when you think about it. What this means is that the membrane is becoming highly permeable to sodium during the peak amplitude of the action potential. There's no doubt about that. But what it also tells you is something else that perhaps is not so surprising. The peak amplitude of the action potential does not equal the sodium equilibrium potential. Why not? You actually know why not. Because the potassium permeability did not go away. The potassium permeability is still there. And that potassium permeability is always trying to make the membrane potential be near the potassium equilibrium potential. So this experiment gave strong experimental support that what was happening was that during the peak of the action potential, the membrane was switching from being at rest, highly permeable to potassium, only slightly permeable to sodium, 1/100th, to during the peak of the action potential becoming highly permeable to sodium. Here's a little schematic diagram of an action potential and some of the key potentials that we have considered so far. Here is the resting potential, minus 60 millivolts as an average value. Here is the sodium equilibrium potential, plus 55. Here is the potassium equilibrium potential, down here at minus 75. A couple of things to note here. Note that the resting potential is not equal to the potassium equilibrium potential. Why not? Because of the slight permeability to sodium, the 1/100th. That's alpha is equal to 0.01 in the Goldman-Hodgkin-Katz equation. Then you have the depolarizing phase of the action potential. Sorry about that. It approaches the sodium equilibrium potential but doesn't get there, and that's because of the resting potassium permeability. Then you have the repolarizing phase, the after hyperpolarization, which approaches, by the way, the potassium equilibrium potential, but never quite gets there, and then you return to the resting potential. The important thing to note here is that the whole trajectory of the action potential, starting from the initiation phase to the termination phase, is bounded on one extreme by the potassium equilibrium potential, and on the other extreme, the sodium equilibrium potential. So it's in this range. And that tells you just theoretically that you could predict any one of these potentials simply by adjusting alpha in the Goldman equation. So if you had a knob on a membrane that changed the relative permeability of sodium and potassium, you could dial in any potential between minus 75 millivolts and plus 55 millivolts. So what we want to ask now is, how does the real cell dial in those different permeabilities to make this action potential? Now, the big breakthrough there came from Hodgkin-Huxley and their colleagues. And what they did was to introduce the concept of a voltage-dependent membrane channel. So what they were saying was that if you made a conceptualize this voltage-dependent membrane channel, it would look something like this. On one axis, there is the depolarization of the membrane. That's the voltage, if you will. And the other axis is the sodium permeability. So what Hodgkin-Huxley and their colleagues were saying was that initially the sodium permeability is very low. But let's say at the resting potential. But if the membrane is depolarized, there is a change in the permeability that's proportional to the depolarization. So you have something that looks like this. Essentially, what they were saying was that you have, go back to my donuts. You have a membrane channel that is intrinsically permeable to sodium. Sodium would like to flow into this channel, but is blocked. If you have a conformational change, though, then the channel will change, open up, and allow the positively charged sodium to come into the cell. So that was the concept of a voltage-dependent membrane channel. Unlike the channel in the rest that underlies the resting potential, it's always open, allows sodium ions and potassium ions to go in and out. This one was special because it's normally closed, but you can open it if you depolarize the cell. Now, how does this scheme account or explain the action potential? Does this help you explain the action potential? It's not intuitively obvious, but let's just step through it. Let me also put up here our old friend, the Goldman-Hodgkin-Katz equation. Vm is equal to 60 times the log of the outside potassium plus alpha times the outside sodium inside potassium plus alpha times the inside sodium. Again, alpha was PNA over PK. Okay, let's just say there's a certain stimulus now. We're at resting potential, and we give a certain depolarization. It can be an artificial depolarization. We'll soon learn about more natural depolarizations produced by synaptic potentials. Now let's walk through this. This initial depolarization, according to this scheme, is going to lead to some opening of the voltage-dependent sodium channels. Then you would have an increase in sodium permeability. Now you need to take the next logical step and ask yourself, if the sodium permeability increases, what would be the consequence of that increase on the membrane potential? It would become more positive, right? Because if we open that channel a little bit, allow some positively charged sodium to come inside, it's going to make the inside of the cell more positive. So as a result of that initial depolarization, albeit a very small depolarization, there'll be an increase in sodium permeability, and that increase in sodium permeability then will produce a greater depolarization. Okay, now you see what's going to happen? That greater depolarization, according to this relationship, is going to produce a greater change in sodium permeability. Then what happens? More depolarized. Greater sodium permeability, more depolarized. And what do we have here? What do we have here? Positive feedback. Somebody's saying positive feedback. It's a positive feedback regenerative cycle. Once we get this thing going, we rapidly depolarize the membrane up to approaching the peak value of the sodium equilibrium potential. Okay, so that's fine. That was the hypothesis. But does it really work this way? So Hodgkin, Huxley, and Katz, they went on to then test this hypothesis. They developed an electronic amplifier called a voltage clamp amplifier. You don't need to know the details of it, but what this device does, it allows one to clamp or maintain the membrane potential at any desired level. So you prevent an action potential from happening, but you measure the changes in permeability or conductance, an electrical equivalent of permeability. So here's an example of the experiment. We're going to look at the membrane potential here, the potassium sodium permeability here, and we're going to change the membrane potential systematically. Start at minus 60, that's here. Then we change the membrane potential to a new value of minus 35 millivolts. And so why they call this the clamp is we change it from minus 60 to minus 35, and it's held fixed there. And then, as a result of that change in potential, we can measure the sodium conductance, which is an electrical measurement of the permeability. And what you see here is that there is an increase in the membrane conductance or permeability. Now you give another depolarization, this time to minus 20 millivolts. Now you see that there's even a greater change in sodium permeability or conductance, and you change the membrane potential to plus 20 millivolts, and there's even a greater change. Now, if you measure this value, and you measure this value, and you measure this value, and you put it on our little graph, you see that the membrane channels are behaving like this. The sodium permeability is a function of the membrane depolarization. So this experiment then was direct experimental proof that there are these voltage-dependent membrane channels that change their permeability as a result of depolarization. We now know the complete amino acid structure of those channels, and we know that there's a conformational change as a result of the depolarization that allows sodium ions to move through them. Okay? So this then is a way of explaining the initiation of the action potential. But there is, yes, sir? G is for conductance, which is the electrical, you can just say that GNA, for convenience, is equal to PNA. The conductance is an electrical measure of permeability. They're not equal, but they're related directly. So this was very nice. It showed that there are voltage-dependent changes in membrane permeability, that sodium ions contribute or are essential to the initiation of the action potential. But there is a little bit of problem with this hypothesis of this positive feedback cycle. And what is the problem with it? You get this cycle going and going and going. Well, how do you get back down again? You need to break the cycle in order to get the repolarization of the action potential. And how you break the cycle, the answer is right before you. Inactivate the channels. Exactly, you inactivate the channels. What do you mean by that? What he means by that is the fact that despite the fact that the membrane potential is held constant throughout each one of these voltage clamp depolarizations, the sodium permeability increases proportionally. But here's the thing. It doesn't stay elevated. It declines, despite the fact that the membrane potential is still depolarized. This process is called inactivation. This part is called activation, and this part is called inactivation. So what this allows one to do then is to break the positive feedback loop. The membrane potential is rapidly depolarized based on this mechanism, but then everything reverses itself back down to the initial membrane permeability. So it's like these channels. You can open them with a depolarization, but then they say, okay, after a while, say, okay, forget it. I'm closing back down again. No more sodium can come through, even though you keep the membrane potential depolarized. So then, does this mechanism allow us to account for the repolarization of the action potential? Is this all we need to know? No. Well, one problem I have with this mechanism is look at the time here. It takes 3 to 4 milliseconds for this inactivation process to do its thing. What's the duration of an action potential? 1 millisecond. So if you only had these kinds of changes, you would think an action potential would be longer in duration than it actually is. Another thing to think about is remember the after hyperpolarization. How can we explain the after hyperpolarization? If we just had this mechanism, how could we explain the after hyperpolarization? In order to get the after hyperpolarization, the sodium permeability would have to go less than what it was initially, because in order to get the after hyperpolarization, the membrane potential is more negative than minus 60 millivolts. The membrane potential comes closer to the potassium equilibrium potential. It comes closer to a membrane that's behaving like it's only permeable to potassium. So there's two problems with this mechanism explaining the repolarization. It's too slow, and it doesn't allow you to have the after hyperpolarization. So there must be something else going on. And that other thing going on is our friend. Here's our friend. Potassium comes to the rescue, because just as there are voltage-dependent changes for sodium permeability, channels that are normally permeable to sodium, but are normally closed, they open with a depolarization. There's channels that are exclusively permeable to potassium, not the resting potential channels, but other membrane channels that are exclusively permeable to potassium, but are normally closed, but open in response to a depolarization. And here's an example of those channels. Now we're measuring both the potassium permeability and the sodium permeability. So here you're going to see exactly the changes you saw before. And now the question is, how does the potassium permeability change? And here's the answer. Here is a depolarization to minus 35 millivolts. Here's your change in sodium permeability. And look, you're seeing changes in potassium permeability as well. Greater depolarization, greater change in potassium permeability, greater depolarization, a greater change in potassium permeability. So just as there are voltage-dependent changes in sodium permeability, there's voltage-dependent changes in potassium permeability. Okay, so now there's two differences between the changes in sodium and the changes in potassium permeability. The similarity, of course, is they're both voltage-dependent channels. They increase their permeability or conductance with a depolarization, and that's what you see here. What are the differences? I don't have to tell you, you can just look at these traces and tell me. Two major differences. One is open longer than the other. Exactly. Note that here is a depolarization, what is it, about 8 milliseconds or so in duration. The sodium channels activate and then they inactivate. But look at the potassium channels. They do not inactivate. They stay open as long as the membrane potential is depolarized. So the sodium channels inactivate, whereas the potassium channels do not. Look at what's happened here, by the way. When you return the membrane potential from, in this case, plus 20 to 0, you see what happens to the potassium channel? It closes. It stays open as long as the depolarization is maintained, but when you remove the depolarization, it closes, and that process is called deactivation, as opposed to inactivation. Here, this is deactivation. Okay, so that's one difference, although I must say that difference is not a critical one. There is another difference that is really important. And somebody said it back there. It takes longer to get there. Where is the there? There's no there. Yes, yes. Is that what you were going to say too? Yes. Look at this. In response to the change in potential right here, there is this immediate change in the sodium conductance or permeability. But the potassium channels, although they open, it's slower than what you get over here. That's exactly right. So the potassium channels open more slowly than do the sodium channels. Is there any importance or significance of that, or is that just some esoteric physiology that only a few people in the world care about? It's essential to have an action potential? Why? It promotes the action potential. How does it promote the action potential? It allows the cell to depolarize without negating itself. You just touched upon the key thing. Well, just think for a moment, ask yourself, what would happen if the sodium channels and the potassium channels opened at the same speed? So if this potassium channel opened at the same speed as that sodium channel, somebody's going like this. They'd cancel each other out. So the opening of the sodium channel would try to depolarize the cell. The opening of the potassium channel would tend to hyperpolarize the cell. The net effect would be 0. So this slight difference in the timing is absolutely essential to make the action potential work. Initially, you have the voltage-dependent sodium channels, which are very fast. Then the potassium channels kick in, and they're actually called, in some terminology, the delayed potassium channels. Delayed because they are a little bit slower than the sodium channels. That allows for the sequence of the action potential. And now with this information, we can actually step through the entire sequence of the action potential, starting with the resting potential and moving on through to the after hyperpolarization. So initially, we have some depolarization. Let's not worry about where that depolarization comes from. We have some depolarization. What we're going to see here is we're going to plot the potassium conductance, the sodium conductance, and the membrane potential. So the depolarization then leads to the increase in the sodium conductance, very little change in the potassium conductance. It's slow. We get this positive feedback cycle. Depolarization increases sodium permeability increases depolarization, and so forth, rapidly moving up to the peak amplitude of the action potential. Then we have two things happening. One is that we have this process of sodium inactivation. The sodium conductance is decreasing. At the same time the sodium conductance is decreasing, now the potassium conductance is increasing dramatically. So this decrease, and this increase leads to the repolarization phase of the action potential. That continues. Now, here's an interesting point. The membrane potential right here is back to where it started. The sodium channels have closed completely. They were open, and now they're completely closed. And now look what's happening to the potassium channels. Just as the potassium channels are slow to open, they're also slow to close. So at this point right here, you see that the sodium channel is back to where it was, but the potassium channel is still highly open. What's the consequence of that? The after hyperpolarization. Now alpha in the Goldman equation is less than 0.01, the net conductance, and so we have the after hyperpolarization phase of the membrane potential right here. Eventually, the potassium conductance returns to zero and the membrane potential returns. So this is a complete cycle of events underlying the initiation, the peak amplitude of the action potential, the repolarization, and the after hyperpolarization. Now, if you didn't believe this, there's some great pharmacologic tools that really illustrate the importance of the sodium and potassium channels and also their specificity. You could argue that they're really not separate channels, that it's a combined channel that allows sodium and potassium to enter sequentially. But there are drugs available that can selectively block one membrane channel and not the other. And one of those drugs is called tetrodotoxin, or TTX. I think you all have that little handout. So tetrodotoxin is isolated from the ovaries of the Japanese pufferfish every year in Japan. It accounts for several deaths due to food poisoning. What tetrodotoxin does is it blocks or plugs up the voltage-dependent sodium channels. Here's a voltage clamp experiment that illustrates the effects of tetrodotoxin. This is the same kind of experiment that we saw previously, changing the membrane potential to these various values and looking at the changes in sodium conductance here, potassium conductance here. You can see in the presence of tetrodotoxin, there are no voltage-dependent changes in sodium permeability, but the changes in potassium permeability are totally normal, indicating that this one agent can block up or plug up the sodium channel, but have no effect on the voltage-dependent potassium channel, and no effect on the resting potential. That's tetrodotoxin. And then there's this other agent called TEA, or tetraethylammonium, TEA. And here you see the consequences of TEA on the voltage-dependent sodium channel and the voltage-dependent potassium channel. The same voltage clamp experiment. Changes in the voltage-dependent sodium permeability are normal, whereas the voltage-dependent changes in potassium permeability are completely blocked. So we have agents that affect one channel, not the other. Now ask yourself, what's the consequence of these agents on the action potential? What do you predict TTX would do to an action potential? No action potential. That's absolutely right. No action potential. And that's why the people who die in Japan because of eating sushi not prepared properly is because their sodium channels are blocked. That means there's no action potentials in their nerves. There's no action potentials that carry messages to their respiratory muscles, and there's no action potentials in their skeletal muscle cells. So it's pretty tough. What would the effect of TEA be on an action potential? So here is a normal action potential right here. You see the depolarizing phase, the repolarizing phase. I shouldn't have. Here's the after hyperpolarization. Here is the action potential in TEA. Note the beginning part of the action potential is pretty much identical to the beginning part of the normal action potential. But what's different is, as your colleague has indicated, it is longer in duration. And note there is no after hyperpolarization. Why is it not infinitely long? It's not infinitely long because we still have the process of sodium inactivation contributing to the repolarization. So with this experiment, you can clearly see how much the potassium is contributing to the repolarization and how much the sodium inactivation is contributing to the repolarization. So you can still have repolarization, it takes longer. Oh, one thing I want to talk about is this issue of the amount of sodium that comes into a cell with an action potential and the amount of potassium that leaves. Clearly, we have these membrane channels, right? And sodium is going to come in as a result of the action potential, and sodium is going to have the conformational change, and sodium is going to come in. Well, how much sodium actually comes into the cell? If you read some textbooks, and I might have been guilty of this myself, you get the impression that there's going to be this big gush of sodium that's going to go into the cell, and it's that positive sodium that makes the inside of the cell positive. Well, that's actually not the case. It's actually a very tiny amount of sodium comes into the cell. The amount of sodium that comes into the cell is in the picomolar range, whereas the normal intracellular sodium is in the millimolar range. So it's minute. It's thousands of the amount of normal sodium. So while you get that charge change across the membrane, the bulk of the sodium concentration has not changed at all. And the bulk of the outside concentration has not changed at all. And that's why the equilibrium potential doesn't change at all, because the equilibrium potential is based on that huge amount of sodium in the inside and the huge amount of sodium on the outside. So some people think, and this is some misinformation in some books, that the sodium pump, the sodium-potassium exchange pump, is important for the repolarization of the action potential. So that's not the case. The sodium-potassium pump is important in the long term to maintain the equilibrium potential. So if you have hundreds of thousands of action potentials, ultimately the amount of sodium that comes in and the amount of potassium that leaves will start to have an effect. And the inside sodium concentration will increase, and the inside potassium concentration will decrease, eventually being the same as the extracellular. It's the sodium pumps, sodium-potassium pumps, that maintains the equilibrium potentials over the long term. It's kind of like the generator in your car. Keeps the batteries charged, but you can run the car for a while without the generator because you can run off the batteries. The batteries are the sodium and sodium equilibrium potential and the potassium equilibrium potential, and the sodium-potassium pump is what keeps the batteries charged. Okay, so the other phenomena we want to talk about are known as the absolute and relative refractory period. So they refer to the time after you initiate one action potential where it's impossible to initiate another action potential no matter how much you depolarize the cell. You cannot get another action potential. It's generally a very small time, fraction of a millisecond after one action potential. Then there's this other time period called the relative refractory period, and that refers to the time after initiating one action potential where it's possible to initiate a second action potential, but only with a greater stimulus. I'm going to make a little diagram of the relative refractory period. So we start off at minus 60 millivolts, right, the resting potential. And then let's say there's some stimulus, a depolarization, that moves the membrane potential to minus 45 millivolts, and that's a common value for threshold. We then initiate an action potential like that, And then we have the hyperpolarizing after potential like that, right? That's the one action potential. This action potential was initiated with a 15 millivolt depolarization. Now assume we use that same 15 millivolt depolarization, but deliver that stimulus at a point in time during the after hyperpolarization. Now that same 15 millivolt stimulus will now be subthreshold. It will fail to reach the threshold because it's only 15 millivolts, and you need 15 millivolts here to get to minus 45, but you need more than 15 millivolts to get to minus 45 if you're starting from something more negative than minus 60. Now, if you were to deliver, however, a larger stimulus, now you could reach threshold and trigger that second action potential. So there's this period of time after the first action potential where it's possible to initiate another action potential, but only with a greater intensity stimulus. So the after hyperpolarization determines, at least in part, this relative refractory period. Now, the absolute refractory period is this period of time immediately after the action potential where no matter how much you depolarize, you cannot get another action potential. How do we explain the absolute refractory period? It's through this process of inactivation that we already talked about, but another aspect of inactivation, and it's called a recovery from inactivation. So here's an experiment that illustrates this process of recovery from inactivation. Here's one voltage clamp depolarization, just as we've seen before. It leads to the opening of the sodium channel and then the process of inactivation. If you deliver a second stimulus at some time, here, what's about 3 milliseconds or so, after the first, deliver another depolarization, you get another change in permeability just like this. These two are essentially identical, right? Now, what's interesting is when you decrease the interval between the first and the second. Now, the second depolarization produces some changes in sodium permeability, but they're smaller than they were initially. If you make this second pulse occur very soon after the first, now that second pulse produces absolutely no change in sodium permeability. It's like the sodium channels weren't even there. So what apparently is happening here is that when you activate and then inactivate a sodium channel, it takes time for that channel to be able to be reopened again. Just can't open so rapidly once it's opened before. So how does this help explain the absolute refractory period? If you give a depolarization soon after the first depolarization, you can't initiate another action potential because all the sodium channels have not recovered from their inactivation. It's like there's no sodium channels there. Only after some time do they recover from their inactivation when a second stimulus can open up those sodium channels again and lead to the initiation of an action potential. Okay, so if you go to your electronic syllabus, there is a simulation program. There are equations that describe the ionic mechanisms of the action potential. You can solve these equations, but the computer simulation does it for you, just as you can have a flight simulator that takes the equations of flight, the lift and the drag and the thrust, and you could solve the equations and simulate flying an airplane. You can have an action potential simulator. You can solve these equations and you could see how the membrane potential changes as a result of changes in sodium conductance and potassium conductance. So here is a normal action potential, and you see the voltage-dependent changes in sodium conductance here and potassium conductance here. And what you can do, which is nice with these simulations, is that you can change some of the parameters. So you can change the maximum sodium conductance. Essentially, that means that's the total number of channels, sodium channels, that are available. The maximum potassium conductance is the total number of potassium channels that are available. There's the sodium equilibrium potential, there's the potassium equilibrium potential, and here's the stimulus intensity. Now, you can use this simulation to test your knowledge. So you can ask yourself, what would be the consequences of changing some of these parameters? How would it affect the action potential? Think about what would be the consequences of making the equilibrium potential, instead of minus 75, making it minus 80. You would need a larger impulse. You might need a larger stimulus, a depolarization to trigger the action potential. Yeah, okay. Are you going to affect the membrane potential? Are you going to affect the after hyperpolarization? Are you going to affect the duration of the action potential? Okay, we've made the membrane potential more negative. Well, we better do that, right? Because that's the membrane potential at rest follows the potassium equilibrium potential. Note we've made the after hyperpolarization more negative. The after hyperpolarization is dependent upon that late increase in potassium permeability. And the stimulus was still sufficient to trigger an action potential, but look, it took a little bit longer to charge up to that threshold value. All right, let's do two more. What if we make the sodium equilibrium potential, instead of plus 55, make it something like plus 30? What do you think is going to happen before we do the simulation? What about the peak amplitude of the action potential? Greater, same, or less? Less. The peak amplitude of the action potential, it approaches the sodium equilibrium potential. If we make the sodium equilibrium potential less, you would think that the peak amplitude of the action potential would be less. It can't get, the peak amplitude of the action potential can't get any greater than the sodium equilibrium potential. It's bounded. Remember, that's as high as it can go. Anything else? The resting membrane potential, why should the resting membrane potential change when you change the sodium equilibrium potential? I thought that was dependent on the potassium equilibrium potential. It's partially dependent on some. Yes, I agree. Anything else will change. All right. There's probably some other changes. Oh, look at the peak amplitude of the action potential. Stop at 30. Look at that. Now the peak amplitude of the action potential is reduced significantly from where it was, right? Look at this. Who said there's going to be a change in the resting potential? It's more negative. Why is it more negative? Well, what's keeping the membrane potential at minus 60 millivolts rather than minus 75? It's because of that slight sodium that's leaking in. If we change the sodium concentration, make it less, that's what we're doing when we make the equilibrium potential less, we're changing the sodium concentration so there'll be less driving force, if you will, for sodium to come into the cell. Okay, let's do one more. What if we reduce the potassium permeability, from whatever this value is, 36 ms, microsiemens, 36 microsiemens will make it something smaller. What will happen if we reduce the potassium conductance or permeability? That's the number of potassium channels that open. It will increase the length or duration of the action potential. This is like adding a drug that we already talked about. This manipulation is the TEA manipulation. That's what we're doing when we change this from 36. Let's start making it smaller. Ooh, look at that action potential. Look at that action potential. The action potential is broader. There's no after hyperpolarization. So you should play with these. Do these simulations yourself. Change some of these parameters, but before you press the button, ask yourself, how is it going to change? And if you're right, then you understand things. Okay, so tomorrow we're going to talk about the propagation of the action potential. If you initiate an action potential in one part of a cell, how does it travel along the axon to the end reaches the synapses? Okay, see you then. Bye.